So let's take a look at um, the 5 bullet points from the Would You Rather to go over each one to talk about how to develop this fluency and flexibility with percentages along paired with, we can use the reasoning from fractions and decimals, so that way we can develop that fluency and flexibility. So we talked about 25% of 300, and we'll just talk about the percentages of. This is not necessarily, or this would be different from than the percentage, like the final price after the discount. So the 25% of 300 would just be the price or the amount of the discount, right? 25% off or discount of 25%. To find then this total price, you'd have to take away that. Or what we'll see is that we can then take 75% of the 300 instead. Yeah, and if that doesn't, you're like, what? Well, we're going to talk about that. So we had these options: 25%. Sorry. Oh no, that was correct. Okay, so we had 25% of 300, 20% of 350, 15% of 400, then 10% of 500, and lastly 5% of 2000. So what we want to see is that I know that you understand how to translate or convert percentages to decimals. And so we can do that. We'll start with the 10% because that's going to be actually one of the easiest numbers to use. And that is a direct result of our base 10 number system, right? Multiplying by tens and dividing by tens is actually is a pretty easy operation because of the way our number system is set up. So this is the same as, right, 0 and 1/10 times, right? The of is the same as times, as we saw with multiplying fractions. So this is 10% of 500, or 1/10 of 500. And so I want to write it in this way and talk about decimals, not saying 0.1 times, but as 1/10 of, to help to develop that the understanding of the structure of these numbers, right? 10% of helps us to see, and then that it's 1/10 of, even if you write it in decimal form. So we want to connect that decimal form to fractions, because we can think about fractions, right, as this division. 500 divided by 10, and now we can see, right, the 10 can go into, right, divides equally into 500. And so you can think about that as 50 times 10 over 1 times 10, and then the tens divide out, right? So then we're just left with 50 over 1, or 50. I know you may have seen a shortcut that can cross out numbers like that, and you might want to say cancel out, but again, we don't want to say cancel out. All right, that's one of our words that we no longer want to say. We want to rephrase that. What happens here, right? What's this operation? Division. So we can divide out, or divide the 10 into the 500. So it's really important that we understand this as an act of division, and not canceling. So now I know you're wondering, okay, so check this out. 10% of 500 is 50. Is 10% of 330? 10% of 220? Yeah, right. So you may also heard of this, or talked about it as this idea of, right, moving the decimal point. But again, I want to caution you, right? That's not true either. The decimal point doesn't move. The decimal point is always between the ones and the tenths place, right? If we're thinking about all the place value chart, the decimal point never moves, right? It's this dividing the place, the numerals in the place value have changed. So that's really important to note, right? The numerals or the place values of the numerals changed place value, right? The 5 is no longer in the hundreds, right? It's now in the tens because, right? Because it was a divided by 10. Dividing by 10, right, is moving place values. And same with multiplying by 10, right? As you you get you group in sets of 10, and as you get 10 in a group, then you move up to the next place value. And so likewise, if you divide, right, take 1/10 of that group, you're going to move down a place value or move to a smaller place value. So make sure you pause the video now, write that down, right? We're not moving the decimal point here. We are, the numerals are changing place values because of our place value system. And maybe, can I add a page? Yeah, look at this, right? So here, I want us to think about our place value system, right? As here's our decimal point. And then we have our ones, our tenths. I should have made this a little bit bigger. Right, we've been seeing this place value chart, and this is, right, ones are 10 to the 0 power. Our tens are 10 to the first power. What's next, right? What are we doing when we're moving this way? Times 10 times 10. So our hundreds is now times 10, or 10 to the second power. And we keep moving up in these bundles of 10 infinitely to the right, right? And likewise, we can now see another pattern. Well, to go from 10 to the third to 10 to the second, or 10 to the second, 10 squared to 10 to the first power, we're dividing by 10. So, or this idea of 1/10, right? Taking 1/10. And so likewise, when we move from the ones to the tenths, right? This is where we get 10 to the negative 1 power, or 1/10, or the 0 and 1/10, right? 0.1. So this pattern continues infinitely. Right? This becomes 1 over 100. This becomes 1 over 1,000, 10 to the negative 2, 10 to the negative 3. And that's because we are in our base 10 number system, right? That's our decimal system, right? Deci, just like decade means 10. So our decimal system is not just because of the literal decimals, like the decimal point, but because of this number 10. And this means we group in sets or bundles of 10. And so if we were in a base 5 number system, these wouldn't be powers, right? We have powers of 10, right? That's what this idea of grouping means. Right? If we were in a different base, here we're in base 10, so we see powers of 10. If we were in base 5, these would all be powers of 5. If we were base 7, they'd be powers of 7. If we were base 60, they'd be powers of 60. So the base determines the power, or the the grouping, the how we group or bundle each of our things, our place values. Sorry, not things. I'm just going to complete this chart. Hundredths, thousandths, right, with the TH. And this would be 10 thousandths. right? 10 to the negative fourth, right? This is oopsie. Sorry, somehow I got onto the eraser. Thousands, right? 10 thousands. So I want you to also see, the patterns, not only going, to the left, right? Times 10 times 10, and even 1/10 times 10 is 1. All right, this will be 1, 10, 10 times 10 or 100, 1,000, 10,000, right? We keep getting bigger by this factor of 10. And likewise, we can keep getting smaller, right? Dividing, taking 1/10 of. All right, so let's go back. So this is why 10% is one of the easier percents to find. Likewise with 100, or sorry, not 100, 100% is the same, right? 1%, right? Instead of moving the decimal point one place, right? And again, we're not moving the decimal point, but shifting the place values one place for 10, we would do it two places for 100, right? Exactly the same as if we were dividing by 100. And that's what 1% means. But we're going to get there. So let's think about, what is the relationship between 10% and 5%? If we look at 10% and 5%, well, 5% is half of 10%. So we can still use this same idea of finding 10%. So this would be 5%, 5 over 100 over 2,000. But maybe I don't know what that is. But I know 1/10 of 2,000, or 10 over 100, if you want to think about that. And then I just want half of that. So we use this flexibility, and again, maybe I should have, let's write it that way. Instead of 1/10, we'll write it as 10 over 100 times 1/2 times 2,000. So we can see this flexibility, right? 5 over 100 is the same as 10 over 100 times a half, right? They're equivalent. And so now we just take 10% of 2,000, or 1/10, of 2,000, and then we take half of it, right? This is the commutative property, just moving the factors around. So 1/10 of 2,000, right? Take your place values and shift them all to the right. We get 200, and now we want half of that for 5%, which is 100. So 5% is always going to be half of 10%. So starting here at finding our 10% of whatever number it is going to be a really great way to start reasoning about percentages, whether it's a percent off or percent of, like if you want to find a tip, right? A 20% tip. Ooh, maybe let's go up here first or next, right? What's the relationship now between 10% and 20%? Instead of half, right, as the 5% was, this is now, right, 2 times. Sorry, that is really terrible. So now let's go up here and talk about, well, again, I know this is 1/10 of 300, but then it's going to be times 2. And maybe we don't like the x's, right? Times 2. Or if that is not really jiving with you, think about it as 20%, 20 over 100 times 300. Now we can simplify. This is either 2/10 right here. We can see that. Or, and if that works for you, great, 2/10 times 300. And maybe you don't know what 2/10 are, but we can still rearrange, right? This is all commutative property, right? This idea of switching the numerators, we saw that in our multiplying fractions task, right? If this is over 1, we can switch those numerators, 300 divided by 10, then times 2. And you can do 2 over 1, but you don't have to, right? If 2's in the numerator, it's always in the numerator. If 10's in the denominator, it's always in the denominator. And same with 300. So now we have 300 divided by 10, which is, go ahead, 30, right? 30 times 2, so that's 60. And so this is what I want you to start seeing is how we think about these percentages, and really comes back to our 10%. Because we can use 10% to figure out almost every other one, the 10% and the 1%. We haven't gotten to 1% yet. So we see 20% is 2 times. We see 5% is half of. So let's use both of the 10% and the 5%, right? 15% is the same thing as 10% plus 5% times 400. So that's the same as, right, 1/10 plus 5/100ths. And now what's this property, right? I'm going to do 10% or 1/10 of 400 plus, right, 5/100ths of 400. And again, come down to the bottom, right? 5/100ths can be the same as, right, 10% cut in half. So I'm writing it this way. You don't have to write this way, but this is how numerically you can show this thought process of first taking 10%, right, 10% of the 400, and then adding it to the 5% of the 400. And maybe I can write that there, right? 10% of 400 plus 5% of 400, right? This is, we're decomposing 15 into 10 and 5. And then using, and we do that, and then we add them together. That's just the distributive property. And so 10% of 400 is 40. Cut that in half. You don't even have to really do any more thinking. Excuse me, half of 40, 20. So this is 60. All right, take a minute. Try another example. Is 15% always going to be 10% plus half of 10%? No matter what number? Yeah, because that's the nature of, right, the number 15. 10 plus 5. Oh man, I was trying to make that look nicer. I didn't do a great job. That's all right. All right, so now we can use this same exact idea to do 25%. We can have, 2 10% plus a 5%. That's great, right? We can do, this is the same as, right, 20% plus 5% of 300. So we can do the 20%, right, as we did. And I know that right, these numbers here are changing. Otherwise, we would have those calculations completed, which would be, again, this 20/10ths or 20/100ths plus 5/100ths. If I can just write. We can use the distributive property, right? 20/100ths times 300 plus 5/100ths. Sorry, my pronunciation isn't the best. 20/100ths times 300 plus 5/100ths times 300. And that's why we would, I know your mouth would rather and your brain would rather say 0.2, but we're going to avoid that. And this is also why we humans invented percents. It's easier to talk about it as 20% than say 20/100ths, right? Percent is per 100. So that we would rather deal with whole numbers. So we've come up with all of these different ways of representing non-whole numbers, right? Decimals and fractions as whole numbers, and in the form of percents. And so we can think about this and do it mentally now. Maybe 10% of 300 is 30, doubled is 60, and then halved, right, is 15. And then that way you can get 75. Another way I want you to think about 25% is literally, right, like 25 cents, a quarter. So this is the same as 1/4 of 300, or 300 divided by 4. And maybe you know that off the top of your head, or maybe this one isn't a great example because it's 300, but if it was 200, boom, you'd know that off the top of your head, right? 200 divided by 4. But even if you don't, you can do this division, or again, I want you to see 25% as the same as dividing by 4, because if it's a multiple of 4, then that makes that that division, maybe available. But that will be the same as 75. Add them together, or do that division on your phone, double check it. All right, so this is getting a little crowded, but I hope you see the power of understanding. I'll kind of cut some of these up, of understanding not only the relationship between fractions, decimals, and percents, but also this idea of multiplicative reasoning, right? We're thinking about it as half of, or double, right, times 2, and looking at these relationships between the percentages. So let's use that same idea to think about, what about any percent? What if we wanted like 27%? Or even like something uglier. Think of something uglier. 68%. And if it was an easy number, or, and I don't like to use the word easy, but if it was like of 100, you would know that, right? But let's see if we could do some reasoning. Let's pick a number that maybe we don't know. And it doesn't have to be super hard, but let's just say something we don't know off the top of our head, like if it was 100. What if it was, what do you want to say? Maybe 120? So let's still keep it not too tough, but these ideas will work for any number, even if it's, even if you get decimals, right? Even if it doesn't divide equally. So take a minute, pause it. How might you approach using these ideas that we just saw, right? In terms of either 10%, 25%, 20%, right? How could we decompose either of these, 27% or 68%, into those easier percentages to find, and then just add them up together? So pause the video, try that. And now let's try it and let's check it out. So the first thing I'm thinking of is 27% as the same as 25% plus 2%. As we talked about, right, 1% is almost equally as easy to find as 10%, because instead of just dividing by 10, we're dividing by 100. So the numerals will shift 2 place values instead of just 1 place value. So again, now we just use our distributive property, right? We're going to do 25% of 120 plus 2% of 120. And then you can rewrite that in any way you like. If you like the percentages because you don't feel like the mouthful of decimals or fractions, awesome. If you're like, that squiggly is going to mess me up because it looks like another number in there and it's not really an operation, maybe you want to write it as, right, 25 hundredths plus, 2 hundredths, right, times these numbers. Maybe you want to write it as fractions, right? 25 over 100, or we can simplify that, right? So again, the power of equivalent fractions and understanding, not an equal sign, plus 2 hundredths. And now we can see this is, right, 120 divided by 4 plus, maybe you can think about this as 120 divided by 100 times 2. If you like it that way, you can think about it as 120, like 1% of 120, then times 2, whichever way you like. And so this is what I mean by, right, when it's the 300 divided by 4, maybe you don't have that off the top of your head, right? Because 30 is not a multiple of 4, but 12 is a multiple of 4. And so 120 is, an accessible multiple of 4, right there at 30. And so now you're like, what do I do this 120 over 100 times 2? So I know you might want to jump right here, right? divide out that 10, that's fine. And if that works for you, awesome. But remember, our language will be divide out, not cancel. So if you haven't written that down, right, we don't say cancel out, we say divide out. And so now we see this as, right, you can see this as 1%, right? 120 divided by 100 is 1% of 120, which is 1 2/10 times 2. And then we get 30 plus 2 4/10, which is 32 4/10. So you may not have known 27% of 120 off the top of your head, but now you can see, just using reasoning, we can think flexibly about decimals, fractions, and percents to help us find any percentage of any number. So so again, pause it. Can you use a similar line of reasoning maybe for 68% of 120? Maybe instead of adding the numbers like we did here, I should have made that, right? We found 25 plus 2 to be 27. Might we think about subtracting? So we can think of 68% of 120 as 70% minus 2% times 120. Right? We can get these multiples of tens, and now we can add and subtract as we would like. You could do even 65% plus, right? 60 plus 5 plus 3%, if that might feel more accessible. There are multiple ways to do it, and that's what I mean by developing this flexibility. So remember, this is the same as, right, we're using the distributive property, 70%, 7/10 of 120, minus now 2/100 of 120. And we already found 2/100 of 120, right? That was over here. So we can think about 70% as 7/10 times 120. And we can, however you like to do the 2%, maybe you know what this is right away, right? We already found that as 2 4/10. So maybe you just want to replace that right there. So now let's think about this 70%, right? Again, this flexibility, 7 is in the numerator and 120 is in the numerator. So we can think about this as 120 tenths, then times 7, minus 2 4/10. And now we see, right, 120 divided by 10, that's just 12 times 7, now minus 2 4/10. 12 times 7, give everybody a minute to remember their 12s facts. 84 minus 2 7/10. And now you like this also right here. Now think about your subtraction strategies. Don't jump right now to 84 minus 2.7 and then having to do, right, all of this crossing out and da 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 da. Try to now again reason about these numbers. Think about it. How many to get to, right? I know they're far away, but 2 7/10, we can go up to 3, right? Add 3/10. We can then go up to 80. Oops. Sorry. Oh yeah, sorry, that's what I wanted to do. We're not going to go up to 80. We're going to go up 80 to 83, and then one more. So we can count up from 2 7/10 to get to 84 to find 81 3/10 is our difference. So I drew out the number line. You don't have to draw out the number line. You can just count out. But I wanted to show you how, right, these same exact methods that we've been using with whole numbers completely translate to decimals. Every single thing that we do with whole numbers translates to decimals because of this same exact pattern. We're still in these powers of 10. So the standard algorithm for adding and subtracting will work. The standard algorithms for multiplying and dividing will work. And so I want you to practice explaining how and why using these ideas here presented right? In our, whether it's a place value chart or just really understanding this idea of, right, the powers of 10 are the same thing as these sets bundles of 10.